Swayam Prabha. Digital India. Educated India.
What is the relevance of the discussion of flow regime for the present discussion, for the present case? It will tell the scope of inviscid flow. Let us first define the inviscid flow, then you will understand why we really discussed the flow regimes. Okay. How do we define inviscid flow? Flow of a viscous fluid. Okay. When I say viscous fluid, any fluid has some viscosity, okay, inherently. So, flow of a viscous fluid, this viscous fluid need not be a very viscous fluid like oil, it could be even water, it could be air as well. Okay. So, flow of a fluid with viscosity in a region of flow in which net viscous forces are negligible compared to pressure, body, inertial forces. Okay. Let us analyze this with the help of the linear momentum balance, and that is the linear momentum balance. The left hand side we have the transient and convection term, right hand side we have the body force and the surface force due to pressure and viscous stresses. Okay. Now, what does this tell you? The net viscous forces are negligible compared to pressure, body, inertial forces. Now, these are the net viscous forces, these terms all of them put together are negligible compared to this pressure force, body force and inertial force as well. Okay. So, when we say inviscid flow, it does not mean that the fluid has no viscosity, that is not the correct definition. Okay. Certainly we cannot have a fluid which has no viscosity. Any fluid is a property of a fluid. So, any fluid will have a viscosity. When we say inviscid flow, look at the terminology, it says inviscid flow, it tells about flow, not about the fluid. Okay. So, when we say flow is inviscid, when the net viscous forces are negligible compared to the pressure, body, inertial forces. Okay. That is what we mean by inviscid flow. Now, what is the relationship between this inviscid flow and the classification of flow in terms of flow regimes? Okay. Now, this inviscid flow occurs when the Reynolds number is high. That is why we discussed about flow regimes. We classified flow regimes based on Reynolds number. At low Reynolds number we have a laminar flow, at high Reynolds number we have turbulent flow. So, inviscid flow occurs under high Reynolds number condition. Okay. Now, next, when we have high Reynolds number, inviscid flow is not present through the entire region. Let us give an example. Let us say we have a flow between parallel plates, or it could be flow in a pipe at high Reynolds number. Okay. When you are near the wall, the viscous forces have a significant contribution. You cannot neglect the viscous forces compared to the pressure, body and inertial forces. So, you do not have inviscid flow in the region near the wall, but in the middle of the pipe or far away from the wall you can neglect the viscous forces compared to the pressure, body, inertial forces. Okay. So, when does inviscid flow occur? First condition is high Reynolds number. Second condition is the region should be away from the wall. Okay. That is why regions away from the wall at high Reynolds number you have inviscid flow. That is why we discussed about the flow regime, so that we understand. I said we have discussed flow regime so that we understand the scope of the present discussion or scope of inviscid flow. So, the inviscid flows occur at high Reynolds number condition, and not alone high Reynolds number, that you should also you can consider flow to be inviscid somewhere in a region away from the wall, not near the wall. Near the wall viscous forces will contribute and you cannot neglect them. Okay. Now, how does the equation simplify? very simple, you just neglect the net viscous forces on the right hand side, which means the entire term will vanish, and that is what is shown here. Left hand side all the terms are written as such, okay, all the terms are written as such. Right hand side you have the body force, the pressure force, but this is negligible, so we neglect it. Okay. So, the terms which will remain to be solved for the inviscid flow are the transient term, the convection term on the left hand side. On the right hand side you have the body force term and the surface force term due to pressure only, okay, that is a difference. Okay. The surface force due to viscous stresses play a negligible role, and we are going to neglect those terms. Now, then left hand side we know we can express as rho dVx by dt, and if you express in vectorial form we have rho and then dV vector by dt, that is the left hand side. Right hand side of course this can be put in vectorial form as rho g vector, and this is minus gradient of P, which we have already done when we discuss the Navier-Stokes equation, okay. And that is called the Euler equation, and that is a photograph shows Euler there, okay. So, what is Euler equation? The linear momentum balance without the viscous force term on the right hand side, okay, or to be more formally net viscous forces per unit volume terms on the right hand side is the Euler equation. When is it valid? At high Reynolds number. Where is it valid? Away from the wall, okay. So, that should be clear the scope of application of the Euler equation, okay. Also like to recall our earlier equation, we have look at that we have gradually evolved in our equation, okay. What do we mean by that? We derived the all encompassing linear momentum balance and then Navier-Stokes equation as well. In terms of application we are slowly evolving. What do we mean by that? The first case, first level of application, the fluid was at rest, so you did not have the left hand side, that was 0, okay, and you had only rho g vector and then gradient of pressure. Even then even that could simplify to only the direction in the vertical direction, okay. Second, when the fluid moved as a rigid body, you have the left hand side, but it was one acceleration term for the entire fluid body. So, left hand side we had rho and dV vector by dt was represented as A vector. Right hand side we have the both the pressure gradient term and the body force. Now, we are not considering the fluid to move in as a rigid body, it can have velocity gradients as well, and that is why we have the I would say full form of the substantial derivative, namely rho dV by dt term on the left hand side, okay. So, that is a gradual evolution from our simple fluids at rest case to fluid under rigid body motion to inviscid flow, okay. Okay. So, let us take one simple application of the Euler equation. This example is not new to us, we have come across this example as an application of differential form of total mass balance or the continuity equation, okay. And this example in fact we used both the integral mass balance and the differential mass balance to arrive at the velocity profiles. Let me just quickly recall the geometry. We have two plates, actual plates are circular, and the bottom plate is porous, okay. Of course, the top plate is a solid plate, and air enters the bottom plate, the porous plate, and flows out in this direction through the sides. If you look at the top view, this is how it looks. So, flow takes place radially and then leaves the plate, and if you look at the front view, this is how it looks. But this geometry involves cylindrical coordinates. So, what we said, we will consider flow between just two parallel plates, but the difference is that the bottom plate is porous and air enters through the bottom plate and flows in these directions. Okay. And now let us read the example. Air flows into the narrow gap of height h, this is the height h, okay, between closely spaced parallel plates through a porous surface as shown. Okay. Assume the flow is incompressible with rho equal to 1.23 kg per meter cube density of air and friction is negligible. Okay. That is a case we are discussing now. When we say friction is negligible, the net viscous force is negligible. Okay. Further, assume the vertical airflow velocity is 15 millimeter per second, this velocity is given to us, and the half width of the cavity, half width is, this is half width, and that length is given as 22 millimeters. The height is given as 1.2 millimeters, it is a small, it is a narrow gap, okay, and we are asked to calculate the pressure gradient at x comma y is equal to L comma h. What does it mean at this point? Okay. The pressure gradient varies depending on the spatial location. X equal to L is this point and x equal to L denotes this location and y equal to h denotes this location. So, that is a point we are interested in where we need to find the pressure gradient. Okay. So, these are recall slides. We applied integral mass balance, we took a control volume from x equal to 0 to x equal to x, did an integral mass balance and found out the expression for the x component of velocity as v naught x by h. X component of velocity increases along the x direction, and then we did a differential mass balance, found out the y component of velocity as v naught into 1 minus y by h. Okay. So, let us take those velocity components. So, velocity field was determined using the integral balance, integral mass balance and the differential mass balance, and these are the velocity components, okay, that we have done already. Now, let us take the Euler equation and see how do we use that to find out the pressure gradient. Okay. So, we will write the Euler equation in the component form, this is in the x direction, this is in the y direction. Okay. To evaluate the x and y component, we need to evaluate the dvx by dt term and dvy by dt term in this on the left hand side. So, let us take dvx by dt, expand and write in this way. We have dou vx by dou t and that is 0, because it is a steady state flow, and then we do have this term Vx and Vx is a function of x only. So, this term also is present. Next term you do have Vy, but Vx is not a function of y, hence this term is 0. Coming to the next term, of course there is no Vz component and Vx is also not a function of z, we are considering only xy direction. So, that term also does not appear. So, we are left with Vx into dou Vx by dou x, and Vx is V naught x by h, dou Vx by dou x is V naught by h, and if you simplify you get V naught squared x by h squared, and that is the dvx by dt term. What does it mean? It tells the acceleration of the fluid particle in the x direction. Okay. Now, let us evaluate dvy by dt, which is the acceleration of the fluid particle in the y direction. We have dou vy by dou t steady state, so that is 0, and next term Vy is a function of only y, so this term is 0, next term also does not contribute. We do have terms for Vy and dou Vy by dou y, and next term V is at a 0, Vy is not a function of z, that is also 0. So, now we will evaluate this term. Vy is V naught into 1 minus y by h, and dou Vy by dou y is minus V naught by h, partial differentiating with respect to y, and if you simplify you get minus V naught squared by h into 1 minus y by h. So, now we are ready to substitute in the x component y component of the Euler equation. Let us do that, and while writing we will bring the pressure gradient term to the left hand side, because we are interested in finding out the pressure gradient, and so dou p by dou x is equal to rho g x minus rho dvx by dt, and we are considering gravity along the y direction. So, g x is 0, so this term is 0, and we will substitute dvx by dt which we have evaluated here, and so we get minus rho V naught squared x by h squared. So, now let us evaluate the pressure gradient in the y direction using the y component of Euler equation. So, let us rearrange and write for dou p by dou y is equal to rho g y minus rho dvy by dt, and g acts along the negative y axis. So, gy is minus g, and we will substitute for dvy by dt which is this term, and so we have a minus here. So, this becomes plus V naught squared by h into 1 minus y by h. So, this two equations tells you the gradient of pressure in the x and y direction, and they are functions of x and y respectively. We are asked to evaluate at the point L comma h. At the point L comma h we will substitute x equal to L and y equal to h, and this expression is obtained by substituting x equal to L here. So, we get minus rho V naught squared L by h squared, and when we substitute y equal to h here, this term becomes 0 and you are left only with minus rho g. So, let us find the numerical values. We are given the density, we are given V naught, we are given the half width, we are given the distance between the two plates. So, let us substitute all in SI units. If you do that, you get the pressure gradient, and this term is the pressure gradient is dou p by dou x I vector plus dou p by dou y j vector, and dou p by dou x is negative, dou p by dou y is also negative. So, you get minus 4.23 I vector minus 12.1 j vector. Look at the unit, it is Newton per meter cube, because pressure is Newton per meter squared. You are looking at the gradient of that, which means divide by one more length unit, you will get Newton per meter cube. Okay. So, what I have seen is a simple application of the Euler equation to find out the pressure gradient under inviscid flow condition, not in general. When the flow is inviscid, then our discussion is valid.